Hi and hello to everyone. In this video we are going to see about the noise, different types of noise in a communication system. Welcome to the lecture. We can classify the noise primarily like thermal noise, partition noise and short noise. Thermal noise is also called Johnson noise. Okay, what about the thermal noise? The first one. See, thermal noise is due to the temperature, right? So it's due to the thermal energy. The electrons will be moving within the conductor in a random fashion. Okay, so because of this random fashion, the average voltage is always zero. Okay, the average voltage is all due to the non-uniform distribution is zero, but it would be associated with the average power, which is not zero, right? So the power due to the thermal noise, which is also called Johnson noise, is given as Pn is equal to kTb, where K is the Boltzmann constant, whose value is 1.38 10 to the power minus 23 joules per Kelvin. B is the bandwidth, which is measured in hertz. T is the temperature, which is measured in Kelvin, right? So this is the expression for thermal noise, power related with the thermal noise, kTb, right? Okay, we can take a very simple problem. What they are saying in this problem is they are taking a receiver whose noise power bandwidth, they are given the bandwidth as 12 kilohertz, and where the receiver is placed, the resistor matches with the receiver input impedance is connected across the antenna terminals. Okay, the receiver is connected across the antenna terminals. Then the question is, what is the power contributed by this resistor in the receiver bandwidth, right? They are asking what is the noise power contributed by this resistor. For this resistor, they want to find out the power due to the temperature. The temperature they are given in is 30 degrees Celsius. They are given in Celsius. Remember, the T we mentioned already in the expression is in Kelvin, right? So the bandwidth is in 12 kilohertz. What about the temperature? The temperature is in Celsius, right? So if you add another 273 degrees Celsius, it will be converted to degree Kelvin, right? So remember, if it is given in Celsius, you have to convert that into Kelvin. That is by just adding 273 degrees Celsius. We will convert the degree Celsius to degree Kelvin. Okay, so temperature is now 303 Kelvin. So use this expression where the power, noise power due to the thermal noise in the resistor is given as kTb, where K is the Boltzmann constant, putting the value here, and the temperature is 303 and the bandwidth is 12 kilohertz. Okay, 12 into 10 power 3. If we compute everything, you'll be getting as 5.0177 in 10 to the power minus 17 watts. It's a very negligibly small quantity. Okay, that is due to the temperature. What is the power? Noise power is very small quantity. Right. Now we have to see, since we know the power, why can't we establish a equivalent circuit for the thermal noise, right? For that, what we are doing is we are taking an equivalent circuit, right? A voltage source in series with the resistance. This is the load resistance. Okay, this together forms the voltage source, right? This is the load resistance. For maximum power transfer, we know the relation. The load resistance should be equal to the source resistance. That is, RL is equal to RS. RL is equal to RS. Since both the resistance are equal, the voltage, total voltage will be equally divided between these two resistors. Okay, so what is the voltage across this resistor? The voltage across this resistor is ES by 2. Okay, right? That is the total voltage ES is divided between two resistors, so the voltage is ES by 2. Okay, so what is the power associated with the load? That is given as voltage EL square divided by RL. What is EL? It is ES by 2 whole square divided by RS. So ES square by 2 square is 4 times RS. Okay, so this is the general expression. Now we can extend this idea for the noise power. Instead of saying the load power, I can replace PL with PN, ES with EN divided by 4R. Okay, right? Using the same analogy, I am going for this, right? So the noise PN is the noise power, EN is the RMS noise voltage, R is the conductor resistance, right? Already the last slide we have seen about noise power due to thermal noise is given as kTb. Shall we equate these two expressions? Okay, thereby you will get the voltage, noise voltage, right? Okay, so on equating En, we are getting this as this value, square root of 4k TB R, where K is the Boltzmann constant, T is the temperature, B is the bandwidth, R is the resistor value. Okay, so the equivalent circuit, that is a voltage equivalent circuit for the thermal voltage, is given as En in series with the resistance, where En is 4k TB R. Okay, and I can, instead of saying as a voltage source, I can represent this as a current source. current source. Okay, what is a current source? A current source in parallel with a resistance. So what is a current? Voltage divided by resistance. This is your voltage En divided by R. The square root of R will get cancelled, so it is getting whole square root of R. Okay, so 1 by R is nothing but G. Okay, I am using a relation. This is the conductance. 1 by R is G. Okay, so 1 by R, 1 by square root of R is 1 by square root of G. Okay, so this is your current In in parallel with the resistance. This is the current source equivalent. Current source equivalent for the thermal noise, right? This equivalent circuit will be helping you to solve the problems, right? Okay, if you have some problem, you can use this. You can use this part of the circuit, connect the rest of the circuit, you can solve it. Clear? Then second type of noise is the partition noise, right? What is a partition noise? If you go by the name, the noise is happening due to the division of current or partition of current, due to the current division between two or more paths, right? If you take a transistor, you know, in a BJT it has 3 terminals, right? Okay, and you take your MOSFET, also all have 3 terminals. Since you have more number of terminals, the current will be divided between the terminals, among the terminals, right? Okay, so that's why this partition noise is greater in the transistor, but it is smaller in the diode. In diode, we don't have any terminals, right? That is, you know, we have only the cathode and anodes we have, right? So there is no division of current. But in a transistor, emitter current is equal to collector current plus base current. The current is getting divided. Okay, that's the reason. Then if you take this sort of transistor, field effect transistor, we know field effect transistor 3 terminals, source, drain and gate. But the gate current is very, very small because gate impedance is very high. Moreover, it is reverse biased, right? So the gate current is very small, means there won't be any partition of noise. Okay, this sort of noise. Okay, this sort of noise is minimum. Partition noise is minimum in FET, right? Whenever there is a division of current is very small, this partition noise is very less. That's the point. Okay, next we move into something called short noise. Okay, what is short noise? It is due to the random variation in the arrival of electrons or holes at the output terminals of an amplifying device, right? See, different electrons or holes arrive at different instant of time. Okay, so this creates some short like sound. Okay, on a metal plate, when you place the iron ball or rolling some iron ball, will get some short sound, right? That's why they are called short noise. Okay, this random varying electrons will arrive at the arrival of electrons at the output terminals of an amplifying device. Randomly it will be arriving. Okay, that is the reason for the short noise, right? So it appears that the randomly varying noise current superimposed at the output, right? This random arrival will cause a noise effect, noise current at the output. Okay, and another point to remember is it has uniform spectral density like the thermal noise, and they have defined the short noise only for the diode, right? That is short noise current for the diode, which is IN square is equal to 2 times I plus 2 I naught QB, right? Where I is the diode current, I can say diode forward current, I naught is the diode reverse current, which is a constant for any diode, right? Q is the charge value, and B is the effective noise bandwidth, right? Okay, but for other devices we have used some approximation to solve it. Only for the diode it has been, short noise has been clearly defined. Okay.